Electrophilic aromatic substitution reaction on benzene. When benzene reacts with any electrophile, it gives substitution product, not the addition product. Benzene is very unreactive. It combines only with very reactive, usually cationic electrophiles. So it gives substitution product, not the addition product. Let us discuss its general mechanism for electrophilic aromatic substitution reaction. So first step is attack of benzene ring on electrophile, that is rate determining step or slow step. Then the formation of cationic intermediate, which is stabilized by resonating structure. And the last step is the fast step, that is abstraction of this proton by its conjugate base and regain of aromaticity of benzene. These are the resonating structure of the cationic intermediate. So what are the summary of general mechanism of electrophilic aromatic substitution reaction? First is generation of electrophile, and second is attack of benzene ring on electrophile. Third step is formation of cationic intermediate, and this cationic intermediate is stabilized by resonance. Fourth is regain of aromaticity of benzene. This is the energy diagram, and the first step is slow step, so it requires high activation and it is high for the first step. Let us discuss various substitution reaction on benzene. First is nitration of benzene. When benzene is treated with nitric acid along with sulfuric acid, it gives nitrobenzene, and its mechanism consists various steps. First is formation of electrophile. Sulfuric acid is more acidic than nitric acid, so it donates its H plus to the lone pair of oxygen of nitric acid. The OH group in nitric acid abstracts this proton of the sulfuric acid and converts into water. Then this water leaves as the leaving group. Then the formation of electrophile, that is nitronium ion, is formed, which is linear. Then benzene attacks on this nitronium ion, so the cationic intermediate is formed. Then abstraction of this hydrogen by its conjugate base form nitrobenzene. Next is sulfonation of benzene. When benzene is treated with sulfuric acid, gives benzene sulfonic acid. Sulfonation with sulfuric acid or SO3 in sulfuric acid converts aromatic benzene into aromatic sulfonic acid. So the electrophile here is SO3 or SO3H+. Here this is the mechanism. One of the sulfuric acid, the OH group, abstracts the proton from another sulfuric acid. Then water acts as a leaving group. Then the formation of electrophile, that is sulfonium ion, SO3H+. Then attack of benzene ring on sulfonium ion forms this cationic intermediate, and then abstraction of proton by its conjugate base, that is SO4- gives benzene sulfonic acid. Alkyl or acyl substituents can be added to the benzene ring. That is the Friedel-Crafts reaction. It involves two reactions. One is alkylation, another is acylation. So this is the alkylation reaction. When benzene is treated with tertiary butyl chloride in presence of anhydrous aluminum chloride, which is the Lewis acid, gives tertiary butyl benzene. First is generation of electrophile. Aluminum chloride is a Lewis acid, so it has vacant p orbital, accepts its lone pair from chlorine, then form this complex by leaving LCl4-. This is the formation of carbocation, which is very stable, tertiary butyl carbocation. So one thing is, we can use also iron chloride FeCl3 or PF3 as Lewis acid. Instead of aluminum chloride, we can use FeCl3 or PF3 as Lewis acid. Then benzene attacks on tertiary butyl carbocation, gives tertiary butyl benzene. There are certain limitations in Friedel-Crafts alkylation. That's our alkylation often gives mixture of products, but acylation stops cleanly after one reaction. Because in alkylation step it is essential that alkyl group can form a cation which can be stable, otherwise reaction does not work very well. So the solution is Friedel-Crafts acylation. This is acylation when benzene is treated with acyl chloride in presence of anhydrous aluminum chloride gives aryl ketone. The mechanism is similar to Friedel-Crafts alkylation but little different. Here the carbocation is formed after leaving of LCl4 minus, but the carbocation is stabilized by plus M effect by conjugation of oxygen's lone pair. But in case of alkylation, the carbocation is formed but it is stabilized by rearrangement or 1 to hydrogen shift. So in Friedel-Crafts alkylation, polysubstituted product are formed. This is the acylium ion. Then benzene react with this acylium ion gives this aryl ketone. So these R may be CH3 or phenyl, etc. If we take R is equal to CH3 or methyl group, the name of this compound is acetophenone. If we take R is phenyl group, the name of the compound is benzophenone. We can convert this aryl ketone into alkyl benzene, that is propyl benzene, by this Clemenson reduction. So the main point is we can prepare alkyl benzene by Friedel-Crafts acylation also. So that's why acylation is more favored than alkylation.